Year 12. This is a lesson on exercise 1C, the Argand diagram. So we're going to have a look at the geometrical representations of complex numbers. So the note says, to geometrically represent complex numbers on number planes, a French mathematician named Jean-Robert Argand has developed the Argand diagram, or the complex number plane. Feel free to use whatever you want to call it. It's like how we label the 2D number plane as the number plane or the Cartesian plane or the XY plane. Different names, same thing. Now this diagram consists of the real axis on the horizontal direction and the imaginary axis on the vertical direction. And any complex number z equals to x plus iy can be represented by a point where the x-coordinate is represented by the real number, the y-coordinate is represented by the imaginary number. So for z equals to x plus iy, it would look like such on an Argand diagram. Now notice how I put a point for the actual number that the complex number represents on the diagram, but I've also done a line through from the origin to the point. And that's just to represent the direction and the distance from the origin, which we will actually call vectors, but because we haven't done that chapter yet, we're going to touch on it later. For now, just get a habit of drawing the line. Some textbooks do dotted lines, but I usually just do a solid line. Let's have a look at some geometrical properties. So first of all, we learned about conjugates. So if I plot z and its conjugate, what would it look like? So just a random point, z equals to x plus iy. Its conjugate would be represented as z bar with the expression x minus iy. And the point z will have x comma y as its position on the number plane. So for its conjugate, it's going to have the same real coordinate, so the x-coordinate, but it's going to go down as I drew it because its real number is a negative version of the original z. So it's going to be plotted to x comma negative y. So then geometrically, we can say that the points z and z bar are reflections. Just want to be specific, so we're going to say reflections across the real axis. Or you can say vertical reflection or across the x-axis, however you want to phrase it. Next property, let's have a look at opposites. So when we say opposites, I'm talking about the negative version of the whole complex number. So imagine having complex number z is equal to x plus iy. Its opposite would be negative z. So that's negative x minus iy. So you can see that whatever coordinates I had for the original x comma y, I now have the negative x and negative y. So my point would be lying there. Zoop. That would be my negative z. So visually, how do you see, what's the similarity or difference between these 2 points? How would you describe them? They're just a rotation of each other. You could say it's a reflection, but then if I say it's a reflection, it's a bit hard to describe the mirror line, the reflection line. So it's easier to say that it's a rotation by 180 degrees. Let's stick to radians. So I'm going to write rotation by pi, and it's important to state the center of rotation. So I'll say rotation by pi about the origin, to be very specific. Third and last property, I believe, if you multiply a vector, if you multiply a complex number by I, what would happen? So first of all, let's just sketch a general number, z equals to x plus iy. If I multiply that complex number by I, then I would get ix plus I squared y, which is just negative y. So if I rearrange that as real versus imaginary, it would look like that. So think about the coordinates of z. I've got the point z as x comma y, and just roughly as using the ratio, I would say that negative y on the real axis sits at around here, and positive x on the imaginary axis would sit around here. And if I try to get the point represented by that, it would be here. So that would be my position for iz. What can we say about z and iz? First of all, I could visually see that it's close to a 90 degree, but is it actually 90 degrees? Is it pi on 2? How can we tell that it's pi on 2? If you thought of a way, you can try it by yourself, but if you didn't pause the video and just kept watching, you would have to use the gradient formula. So you can easily just use these coordinates to compare the gradients, and you'll see that the two gradients are, they multiply to -1. So we can say that those 2 points, I should be saying vectors, but those 2 lines would be perpendicular. They meet at right angles at the origin. So then if they do meet at right angles, I can say that point iz would be the original point z that has been rotated by 90 degrees, but I'll be very specific, rotated anti-clockwise because we moved to the left, anti-clockwise by pi on 2 about the origin. And notice how for the previous one I didn't necessarily state the direction of the rotation, and that's because it was a rotation by pi. Doesn't matter if it's anti-clockwise or clockwise. Okay, let's try some examples together. These examples should be fairly simple at the beginning, so feel free to pause the video and try by yourself. Okay. The example says if z1 is equal to 5 plus 2i, z2 is 1 plus 3i, show the following. So, in order to sketch z1 bar, I will probably sketch z1 first. I'm trying to use one little square as one unit, so that's z1. And if I have z1 bar, that's going to be a reflection across the real axis. So there is my z1 bar. For the opposite, negative z1. First of all, here is my z1, and negative z1 would be a rotation by pi, so it would be sitting somewhere here. Oh, not a conjugate. Negative z1. For I z1, again, I need to sketch z1 first and rotate it anti-clockwise by pi on 2. So I would end up at basically at -2,5, isn't it? I z1. Quick and simple. Now for I cubed z1, you can think about it in 2 ways, I guess. By the fact that I has been multiplied to z1 3 times, we can think of it as a rotation done 3 times. So if this is my z1, that would have been iz, that would have been I squared z, which is equivalent to negative z1. And if I do another rotation, it's basically a rotation by 270 degrees anti-clockwise, or you can think about it clockwise 90 degrees, of course. But anyways, it would end up at 2, -5. Or simply, you could have simplified this to negative iz1. So you rotate it and you rotate it twice. So I guess it's like the same thing anyways. Just depends on the order of how you think about it. For the next one, z1 plus z2, you can literally just simplify the expression. So let's go above to the question. z1 plus z2, if you add the real components, it's 6. Imaginary would be 5i. So you just have to literally plot that point. So 6 plus 5i, we would be at here. Oh, I'll just do a line. 6 plus 5i. And then for z1 minus z2, it would be 5 minus 1, 4, 2 minus 3, -1. So I've got 4 minus I, and if I represent that on the Argand diagram, it's going to be... Oh, whoa, what did I do? 4, -1, basically. Done! I hope you guys found these ones pretty simple and straightforward. It's basically just plotting points, isn't it? Now, these are more of the common types of questions you'll see in the exam. For other types of curves, sometimes you just need to interpret the geometrical meaning of the equations. For example, if it says to graph real of z is equal to 3, think about it as in the expression z equals to x plus iy, you want the real part to be 3. So I could translate that as you want the x to be 3, or you want all the collection of points where the real coordinate is 3. So that would be a vertical line through 3. For the second one, it says the imaginary part of z has to be -2. So again, if we want this part to be -2, then we want the y to be -2. That you can already see what it looks like. It's a horizontal line through -2. So you can just literally interpret what it means geometrically. For the next example, find the locus of all z equals to x plus iy, where z times by conjugate z is equal to 4. And we need to sketch. Now the word locus, not a popular word these days, not in the syllabus, but it's in the topic guidance. So I think I need to introduce it to you. It's basically a set of all points that satisfy the conditions. So think about it as the same thing as find the curve described by this equation. Means the same thing. So let's think about the meaning of this equation. What does it mean for z times z bar to be 4? Now we can expand it out using z equals to x plus iy. So z times z bar would be x plus iy times by x minus iy. And using the sum of squares, we know it's going to be x squared plus y squared. Happy for you to expand it out all by term by term. And for that to equal to 4, what does this look like? It's just a circle equation with center at the origin and radius 2. So circle at the origin, or center at the origin, intercepts at 2 and -2. So sometimes you have to interpret it, simplify the expression, and then see what the Cartesian looks like. Last example for today. It says describe and sketch the curve defined by that. So again, we'll need to look into what that means. First of all, we've got fractions. If I see addition of fractions, I just like to add them together to make one fraction. But before I do so, let me state the conditions. We cannot have z and z bar being 0 because it's on the denominator. I might box that. And then let's collect the fractions together. So common denominator, move the denominator to the other side. And then at this stage, I could probably replace the expression with the coordinates. So that's going to be x minus iy plus x plus iy is equal to the product. And simplifying this equation down, we'll get 2x is equal to x squared plus y squared. Now that sort of looks like a circular equation, but not. So the trick is we collect everything to one side. Then because I've got x squared and minus 2x, I must be collecting them as a perfect square. So let's make them into perfect squares by completing the square. Can I just do it in one step? That one has to be x minus 1 squared, and that would have needed a constant 1 on the right hand side. So add 1 to the left hand side. The y squared doesn't really have any other y terms, so it just stays like that. So what do you see? So this one is also a circle equation, but the center is at 1, 0, and the radius is 1. So the circle should be going through the origin like this, center 1, and I might just label all the end points. But going back to the natural domain, I don't know if I should call it domain because it's not just the x values, but because z and z bar can't be 0, technically I don't think we should have a plot there. So at the origin I should have the empty plot, and that completes the graph. So when you guys do the exercise, make sure you try and simplify the equations down and understand what it has to be geometrically. Okay, that's it for the lesson. Your homework is on exercise 1C. Try the following questions and let me know via email if you have any inquiries. Have fun!